Hi everyone. Today we're going to be discussing a very central question when relating to inorganic chemistry, specifically when a complex is going to be square planar versus tetrahedral, and it all comes down to understanding the crystal field of that complex. Now, I just pose a question here as kind of an opener to this section. Why is nickel with 4 cyanide groups, why is that complex square planar? Why nickel tetrachloride is tetrahedral? So nickel forms a complex where it looks something like this with the cyanide. So for nickel, you'll observe this very planar structure to it. However, when we deal with nickel trichloride, it looks like that. Now let me go grab another whiteboard because I want to write some notes down. Bring in my other whiteboard here. So we're going to discuss two fundamental principles which will define if you have square planar tetrahedral. Now the first one is steric hindrance. Now let's just look at the differences between a square planar versus a tetrahedral. Now notice at the bottom, now this one I'm looking at an aerial view, right? This is going to be your square planar. The bond angle between any two ligands on that complex is going to be 90 degrees. However, if we look at a tetrahedral geometry, we know that this will always be 109.5 roughly. And that's for any two ligands. So any ligands in a tetrahedral geometry will be 109.5 degrees apart. So what does this mean for sterics? Well, this is your first consideration. If you have really big, bulky ligands, say for example, triphenylphosphine ligands, something like that, right? You're definitely going to want a tetrahedral geometry over square planar just because of steric hindrance. Hopefully this is something that you've learned in organic chemistry, is steric hindrance kind of is going to want to push groups as far away as possible, right? Maybe you did that when you were determining how does a nucleophile attack? How does the final atom arrange itself, right? Same kind of concept here. We're going to notice that big, bulky groups are going to prefer tetrahedral, while small groups will prefer square planar, but that's not the only factor. And for this next part, we have to look at what's called the crystal field splitting energy. Hopefully you have some familiarity with that. If not, please watch a video on the crystal field theory, specifically relating to how square planar and tetrahedral works. But it's quite simple. We're just going to draw a crystal field splitting energy diagram. Okay, this first one will be for square planar. And we know that there's a really high d orbital here, I believe dx squared minus y squared, followed by relatively closer in energy other orbitals here. Okay, that's for square planar. Now compare this instead to tetrahedral. Okay, so if we look at tetrahedral now, things are going to change, right? We have the T2G orbitals, right? I won't draw out everyone, but the T2G orbitals go there, while on the bottom we have EG orbitals, so dz squared, dx squared minus y squared. Okay, those are lower in energy than the T2Gs, and that's for a tetrahedral complex. Now what you're going to notice is that square planar complexes are formed under very, very, very specific conditions, and that's when you have D8 low spin. Okay, so when your metal is D8 and you have low spin, meaning that you have really strong ligands. Okay, so if you have really, really strong ligands, you have low spin. Hopefully you remember that. And that just means that before you jump up to the higher energy orbitals, you fill the lower energy orbitals. So low spin because of strong ligands, and you're also D8, and we'll see why. So let's assume that we have D8, and in this case, nickel is D8 in its 2+ form. If you look back at what we have here, you can check for yourself, but those complexes are D8. So that's kind of important going forwards. Now, let's fill in 8d electrons into the complex here. Now, if we notice D8, in the low spin square planar, we're going to fill each orbital together instead of filling them all equally. There's a principle for that, I always forget it, the name of it, but the one that you fill each one before you start pairing, you don't do that with low spin, you pair them up as you go. So D8 is going to look like this, and I want you just to notice, we'll get to why this is important, but notice the large crystal field splitting energy here. So I'll just put delta E to signify there's an energy difference there, and it's quite large, you'll notice, quite large. In comparison, if we have low spin, with tetrahedral, it actually doesn't matter. You can fill, you fill them as if they were high spin, because the crystal field splitting energy is so close. So 1, 2, 3, 4, 5, 6, 7, 8. And what you're going to notice is that the crystal field splitting energy here is a lot lower. Okay, the crystal field splitting energy here is a lot lower. Well, actually, that doesn't really matter for what we're going to get into. But I want you to notice how these electrons are arranged. The delta E from here to here is really large, and because of that, it's not going to want to fill electrons up here. So notice what that does to the average energy of any electron in the d orbitals. It's going to lower, okay, compared to tetrahedral. If we look, if you took the average of all the energies of all electrons, you would find that those electrons in those orbitals on average have less energy. So sp d8, you get lower energy d electrons. However, if we compare this to tetrahedral, notice on average, and this isn't really drawn to scale, these T2G might be a little higher. However, because you have these really high energy orbitals and only a few lower energy orbitals in comparison here, you're going to, on average, for tetrahedral D8 low spin, tetrahedral D8, assume low spin, you're going to find that these electrons compared to these ones are higher in energy. So these are higher Okay, so hopefully you see the difference. In square planar, the D8 low spin electrons are lower in energy, but however, tetrahedral D8 electrons with low spin doesn't matter, but it would be higher energy electrons. Now, if the D8 complex had high spin, this would be a different case. You would get tetrahedral, but in this very specific case, because all these electrons are lower in energy than these ones, we're going to notice that for D8 low spin compounds with strong ligands, that's assumed, you're going to get square planar compounds. So hopefully you can follow that. But I now want to get back to our initial question that we opened with. Why is nickel with 4 cyano groups square planar while nickel tetrachloride is tetrahedral? Well, if you remember the spectrochemical series, right, CN is a stronger ligand than Cl. So nickel with the 4 cyano groups has strong ligands, while the nickel tetrachloride 2- has weak ligands And that's all it comes down to, really. But also notice that nickel is D8. So that's kind of the explanation I want to leave you with. If you can follow what I said on the board, then you can follow this here. Nickel with the 4 cyano groups has strong ligands. It's going to exhibit low spin, and it's nickel D8. And because of that crystal field splitting energy, those electrons on average are a lot lower in energy. While nickel tetrachloride is the opposite. It has weak ligands, you get high spin, and it's going to prefer a tetrahedral geometry. So hopefully you guys enjoyed this video. If you did, please drop a like, comment, and subscribe. Greatly appreciate it. Have a wonderful day. Bye-bye.